right, ready to dive into some inductive logic,
Always up for a good logical deep dive.
especially when it comes to how evidence, actually supports those scientific hypotheses.
Yeah.
It's kind of a big deal for how we build knowledge in science. And as a philosopher, I think you'll find this really gets those philosophical gears turning.
Absolutely. It's a question that's been at the heart of philosophy for ages, right?
Hmm.
How do we go from what we observe to what we can actually justifiably believe about the world? And inductive logic, especially the Bayesian approach we'll be looking at today, gives us a really powerful way to think about that whole process.
Okay, so before we get lost in the details, can you give us like the big picture of what makes inductive logic different, especially for someone who's already spent a lot of time thinking about philosophical reasoning?
Sure. So, unlike deductive logic, where if you have true premises, your conclusion is guaranteed, inductive logic is all about arguments where the premises give you support for the conclusion, but they don't 100% guarantee it's true. It's more about degrees of support, not about those airtight proofs.
Right, it's about weighing evidence and dealing with uncertainty, which I think is much closer to how we actually reason in everyday life. And in science, too, like you said.
Exactly. And that's where that Sherlock Holmes comparison, the one that pops up in our sources a lot, becomes really interesting. You know that famous line, when you have eliminated all, which is impossible.
Oh, yeah,
Yeah.
classic Sherlock. But isn't that kind of an idealized view of inductive reasoning? I mean, can we really eliminate all other possibilities?
Well, probably not perfectly. No, you're right about that. But the basic idea behind what Holmes is saying is actually really important for this. Bayesian inductive logic aims to make the true hypothesis very probable by systematically making all those competing hypotheses less plausible. We're trying to narrow it down.
So it's like we're refining what we believe based on the evidence and getting rid of the unlikely options as we go.
Yeah. Exactly. It's all about getting more and more certain. Now, our sources talk a lot about something called Bayesian logic as this important way of doing inductive reasoning. Can you give us the rundown on that? What are the basic building blocks?
Okay, so picture this. At the heart of Bayesian logic, you've got three things: prior probabilities, likelihoods, and posterior probabilities.
Yeah.
It's like a system where what we believe changes and adapts based on the new evidence that we get.
All right, let's break those down one by one. Let's start with prior probabilities. What exactly are we talking about there?
So prior probabilities, that's just a fancy way of saying how plausible we think a hypothesis is before we actually have any new evidence. It's our starting point based on what we already know, or maybe even what our gut tells us.
So it's not just about the evidence by itself, but about how that evidence fits into what we already know.
Exactly. Our existing beliefs definitely color how we see new information. Now, those likelihoods, those come in when we look at the new evidence. A likelihood basically tells us how well the evidence we see actually matches up with a specific hypothesis. So it's like asking, if this hypothesis is true, how likely is it that I would see this evidence?
You got it. And that brings us to the posterior probabilities. Those are the updated beliefs about the hypothesis after we've considered both the prior probability and the likelihood of the evidence.
So it's like a mix of what we thought before and what the new information is telling us. We adjust our beliefs based on how well the evidence fits with what we already thought.
Precisely. Bayesian logic gives us a way to put all these pieces together and come to more solid and nuanced conclusions. It's pretty cool.
Now, our sources mention these two rules, Rule RB and Rule OB, that govern Bayesian inference. They sound a little technical. Can you break them down for us without getting too complicated?
Of course. These rules are basically the math behind how prior probabilities, likelihoods, and posterior probabilities all work together. Rule RB, which stands for the ratio form of Bayes' theorem, focuses on how the ratio of likelihoods for two competing hypotheses actually changes how strong our beliefs are after we consider the evidence.
So we're comparing how well different hypotheses explain the evidence.
Exactly. And Rule OB, the odds form of Bayes' theorem, takes this a step further and lets us think about more than just two hypotheses at once, like a whole range of possibilities. It helps us calculate the posterior probability for each one individually.
Ah, so it's not just an either situation, but we can consider all sorts of options.
That's right. And from a philosophical standpoint, what's really cool about these rules is that they show how our initial beliefs, those prior probabilities, really do affect how we change our minds when we get new evidence.
Yeah, it makes you think that this framework could be really helpful for breaking down and analyzing philosophical arguments, where we're always weighing different ideas and trying to figure out which ones are best supported.
You're absolutely right. That's something we can definitely explore more later. But before we get ahead of ourselves, let's talk about another important part of Bayesian logic interval estimation.
Okay, that sounds interesting. What's interval estimation all about?
Well, sometimes we're not trying to find just one true hypothesis. Instead, we want to figure out the probability that the truth lies somewhere within a certain range of possibilities.
So we're acknowledging that we might not have the exact answer, but we can still estimate how likely it is that the answer is within a certain set of options.
Exactly. Bayesian logic gives us tools to do this kind of estimation. Rule BED is for when we're dealing with separate hypotheses, while Rule BEC is for when we're dealing with a continuous range of possibilities.
So instead of saying that a particular philosophical theory is definitely true, we might use these rules to figure out how likely it is that the truth is somewhere within a certain set of interpretations of that theory.
You got it. This approach helps us deal with uncertainty, which is everywhere in philosophy, where it's hard to be absolutely sure about anything.
Now, as we're getting into this Bayesian reasoning, I'm wondering about something our sources mention. Auxiliary hypotheses. What are those, and why are they something to watch out for?
Auxiliary hypotheses are basically extra assumptions or background beliefs that we need to connect the main hypothesis to the evidence. They're like the bridge between our theory and what we actually observe.
I see they're kind of like the supporting actors, but could those auxiliary hypotheses be manipulated or chosen in a way that biases the results toward a specific conclusion?
That's a really sharp question, and philosophers of science have been thinking about that a lot. It's definitely a concern that we could use these auxiliary hypotheses to prop up a theory we like, even if the evidence itself isn't that strong.
So there's a chance for bias if we're not careful about how we choose and justify those extra assumptions.
For sure. But the good thing about the Bayesian approach is that it forces us to look at those auxiliary hypotheses with a critical eye, too. They can't just be random or chosen to fit what we want to believe.
Okay, so there's a kind of built-in check. We don't just accept those auxiliary hypotheses on faith, but actually evaluate how plausible they are based on the evidence.
Exactly. That helps us avoid bias and make sure that our conclusions are based on solid reasoning.
I'm starting to see how much careful thinking goes into Bayesian logic. It's not just about accepting the evidence at face value, but thinking about our prior beliefs, the likelihoods, and even carefully scrutinizing those connecting hypotheses.
Right. And as we'll see in our upcoming examples, this whole framework is really useful for understanding how evidence shapes what we believe, not only in science, but potentially in philosophy as well.
Well, on that note, let's move on to some real-world examples. I'm excited to see how this Bayesian stuff works in practice.
Let's jump into a big one, something you'll be familiar with as a philosopher, Einstein's general theory of relativity.
Yeah.
And how it basically, took over from Newtonian physics.
Yeah, talk about a game changer.
Yeah.
How did this Bayesian stuff help us understand that whole revolution in science? It had a big impact on how we think about space and time and gravity, right? All those big philosophical questions.
Huge, absolutely. One of the things that general relativity predicted, and this was different from Newton, was that light, even though it doesn't have mass, would be bent by the gravity of really massive objects like the sun.
So it's not just the evidence itself, but how it fits or doesn't fit with what we already think is true. Newton's model was working pretty well for a long time. This new idea must have ruffled some feathers back then.
Oh, yeah, totally. To test this out, astronomers needed to see starlight that was passing really close to the sun, which is not easy to do.
Right. The sun's pretty bright. Hard to see those tiny stars next to it.
Yeah, but our sources talk about how they used a total solar eclipse to do it.
Ah, that's clever. During a total eclipse, the moon blocks out the sun's light so you can actually see the stars near the edge. It's like nature gave them a perfect moment to test Einstein's theory.
Exactly. So in 1919, there were these two expeditions led by Arthur Eddington and Andrew Crumlin. They went to different parts of the world to watch the eclipse and took pictures of the stars near the sun, like a big science adventure.
Okay, so they got the evidence, but how did they actually use it to decide if Einstein was right? I mean, measurements aren't perfect, right?
Yeah.
There's always some uncertainty.
That's where those likelihoods come in. And the whole idea of statistical error. The astronomers had to figure out how likely their observations were given what each theory Einstein's and Newton's predicted. They had to account for the fact that their measurements weren't perfect.
Right, so they're saying if Einstein is right,
Yeah.
how likely is it that we'd see this data? And if Newton is right, how likely is it? They're comparing the two.
Exactly. And get this, the results were totally on Einstein's side. The likelihood of seeing that starlight bending the way it did, it was way higher if Einstein was right. It was so convincing that a lot of scientists who had thought Newton was right all along started to change their minds.
It's amazing how strong evidence can change even our deepest beliefs about how the universe works. And it shows how this Bayesian framework helps us see how evidence and our prior beliefs work together.
It's a two-way street. And this idea of prior probabilities, it pops up even in less, universe-shattering stuff, like the example of COVID-19 self-tests that our sources talk about.
Oh yeah, those things have become part of our lives now. What's the Bayesian take on those? How do prior probabilities matter when you're looking at the results?
Okay, imagine you take a COVID test at home and it comes back positive.
Not the news you want to hear.
No, not really. But anyway, the likelihood of getting that positive result, it depends on how good the test is, right? Like how often it correctly identifies people with COVID and people without it. There's usually some statistics on the box.
Yeah, you always hope those numbers are good.
Right, but there's something else to think about. The prior probability. In this case, that means how many people in your area actually have COVID when you take the test. That's where things can get a little tricky.
So even if the test itself is good, your chances of actually having COVID might not be that high, depending on how much the virus is spreading around you.
Exactly. If COVID isn't very common where you live, even a good test can give you a false positive. So your initial belief, the prior probability before you even take the test, should be that you probably don't have COVID. That, plus the test result, gives you the posterior probability, which is your updated belief after thinking about all the evidence.
So those test results, you have to take them with a grain of salt. You got to consider the big picture, like how common the disease actually is. This seems like it could be really relevant in philosophy too, right? When we're
Yeah,
dealing with ideas that you can't just measure like a virus or a star's position.
absolutely. Which brings us to another cool example, continental drift.
Ah, yeah, the idea that all the continents were once one giant landmass that slowly broke apart over millions of years. How does Bayesian reasoning apply to something like that, where the evidence isn't about precise measurements, but about patterns and geological stuff?
It's trickier to put exact numbers on the evidence for continental drift, you're right. But Bayesian logic still helps us see which hypothesis is better supported. Think about the stuff that proponents of continental drift pointed to. The coastlines of Africa and South America, they kind of fit together like puzzle pieces. And you find the same types of rocks and fossils on continents that are now separated by oceans.
Right. It all fits together, literally. But you can't just calculate the likelihood of continents fitting or fossils being in the same place, right?
Right.
So how do you use Bayesian logic here?
The key is that, even without exact numbers, experts could still see that those observations were way more likely if continental drift was true. The older idea that the continents were fixed just couldn't explain it as well, so the likelihoods might be fuzzy, but their ratio, how much more likely one hypothesis is than the other, that really pointed toward drift.
I see. It's about making smart comparisons, even if you don't have exact numbers. Bayesian reasoning is pretty flexible, huh?
It is, and that makes you wonder, could we use this kind of thinking to look at philosophical arguments too, where a lot of the evidence is about logic and reasoning, not just numbers?
That's a great point. And speaking of good examples, I think we have one more from our sources that really gets at the heart of this whole inductive logic thing. It has to do with developing new medical treatments. Like, how do we know if a new drug actually works? It seems like a perfect example of inductive logic in action.
It totally is. Imagine, okay, so you have these researchers, they're working on this new drug for some disease, right? And the hypothesis is that this drug, it's going to be effective, it's going to help people. And that hypothesis, it comes from what they already know about the disease, how they think the drug works in the body, maybe some early tests they've done in the lab.
So all of that, plus any research that's already been done, that's their prior probability, how much they believe the drug will work before they actually start testing it on people.
Right. So to really test it out, they do a clinical trial. It's like a carefully controlled experiment where they give the new drug to some people and then either a placebo, like a sugar pill, or a standard treatment to others, and then they compare how everyone does. That's the likelihood in this case.
They're looking at the evidence to see, okay, do the results match up with the idea that the drug is actually doing something?
Right. And it's not just about the numbers, right? It's about how strong the evidence is. They have to think about things like how big is the effect? Are the findings statistically significant? Could there be any bias or errors in the way they design the trial? All that stuff.
So they're taking all that new evidence and combining it with what they already knew. They're constantly updating their beliefs. That's the whole prior probability, posterior probability thing, right?
Yeah. That's the heart of it. And it shows that inductive reasoning, it's not just a one-time thing, it's a process. Scientists, they don't just say proven or disproven after one study. They keep gathering evidence, and their understanding keeps evolving. Each new piece of information adds to the overall weight of the evidence, making the hypothesis more or less likely.
It's like building a case, one study at a time, adding more and more bricks to the wall of scientific knowledge. This Bayesian framework really helps you see how all the pieces fit together.
It's like a puzzle, for sure. And this brings us back to your earlier point about applying Bayesian reasoning to philosophy. I mean, philosophy is all about those big questions that you can't just answer with a lab experiment, right? Things like consciousness, free will, morality.
Yeah, those are tough ones.
Yeah.
No easy answers there.
Definitely not. But you do have evidence, in a way. Things like introspection, those aha moments when you think about yourself, logical arguments, thought experiments, what if this happened, what if that happened, looking at how philosophy has developed over time, even observing how people behave.
Right, there's all sorts of evidence, even if it's not the kind you can measure in a test tube. So how could we use this Bayesian lens to look at those big philosophical questions?
That's a good question. Where would those prior probabilities, likelihoods, and all that fit in?
Well, I guess the prior probabilities would be like our starting point, right?
Right.
What we already believe about the issue based on our own intuitions, what other philosophers have said, and so on. And then the likelihoods, that's where we look at all those philosophical arguments and theories and see how well they fit with what we already think, how logically sound they are, whether they have any holes in them.
So it's like we're running thought experiments in our minds, comparing different lines of reasoning, seeing which ones make the most sense based on our initial assumptions.
Exactly. And then the posterior probabilities, those are our updated beliefs after we've done all that thinking and weighing the evidence. It's not going to be a simple calculation because philosophical arguments can get pretty messy. But this Bayesian way of thinking could still be helpful. It could help us be more clear about our assumptions, see where we need to think more deeply, or maybe even gather more evidence.
I like that. It means that even in philosophy, where it's hard to be totally certain about anything, we can still be rigorous and systematic in how we approach those big questions. There's a structure there we can follow.
And that really gets to the core of inductive logic, whether we're talking about science or philosophy. It's about recognizing that knowledge is a journey, not a destination. We start where we are, we gather evidence, we weigh the possibilities, and we keep adjusting our beliefs as we go.
It's all about exploration, critical thinking, being open to changing your mind when you learn something new. And that's something that both scientists and philosophers have in common. They're both seekers, in a way.
Well said. Well, I think that wraps up our deep dive into inductive logic for today. Hopefully our listener, armed with these Bayesian tools and a better understanding of how evidence and belief revision work, feels ready to tackle those big questions, whether they're in science or philosophy, with a more critical and insightful mind.
It's been a great conversation, really thought-provoking. And to our listener, remember, the world's full of mysteries and challenges, and inductive logic is a powerful way to navigate them. It helps us understand the evidence, make sense of things, and keep pushing the boundaries of what we know.
Couldn't said it better myself. Thanks for joining us on this deep dive. Until next time, keep those minds curious and keep searching for those answers.